All right, everybody, we are ready to get started here. Welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today. I'm in the pilot's booth, which is at the top of the room, waving my arms. Hello, everybody. Welcome. And today I'm so excited because you are all seeing our last show of the day, which is one of my favorites to give because it is a completely live show. So the rest of the shows that we have throughout the day are pre-recorded movies, kind of with a short portion where I can update you on a particular topic. This show is a bit different. This show is completely live, so I'm going to be talking to you for the next 20-ish minutes or so. We're going to fly around the universe together. We're going to start out at Earth and zoom out as far as we can out into space and come back safely home at the end of the show. All right, so we are starting our tour of the universe relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And I always like to start us out at the International Space Station to give us a little bit of perspective on the incredible distances that we are going to cover today. Because today we're going to fly out as far as into space as we can, like I mentioned, and along the way, we're going to check in on our human influence out there in space. So we're going to see things like how far have humans traveled into space, how far have our spacecraft traveled, how far have our communications traveled, and we are going to travel much faster and much farther than any of that. But the International Space Station, this is as far as humans travel out into space right now. You can fit about 6 or so astronauts on the ISS at any one time. And we've had people living up there for about 20 years now. But don't worry, it's not just 6 people that have been stuck up there for 20 years. They do swap out every few months or so. And the longest that any particular astronaut has lived up there was about a year. But this is as far as humans travel into space right now, pretty close by, just a few hundred miles above the Earth's surface, and traveling very quickly. I'm going to bring up our yellow line here to show us where the orbit of the International Space Station is. And it only takes them about 90 minutes to orbit us once, so they're going around us very, very quickly. But as we zoom away, I'm not going to stay at any one particular spot too long throughout the show because we have a long distance to cover. So we're going to keep going at a pretty quick pace here. And as I zoom away from the International Space Station, we'll start to see some of the other features of our planet show up, things like clouds and our atmosphere. And something I do want to point out about everything that we're going to see here today is that this is all based on real data and pictures of the locations that we're going to visit. So for example, the clouds and such that you're seeing around the Earth, these are where these clouds and weather patterns were early today, because all of this is using the OpenSpace software, which is a free open source planetarium software that you can download at home. And so the clouds you're seeing, those are all data and images that were taken from satellites that are going around our planet. So if you want to download that when you get home, you can. And you can see that they haven't updated the data for the bottom part of the Earth that we're looking at right now. But I'm going to zoom us away to visit our closest natural neighbor in space. And I say natural neighbor because, like the International Space Station and all the other human-made satellites we have around us, we have a lot of human-made neighbors as well. But I'm going to take us over to our natural satellite, the moon. And when I change focus, it might switch kind of quickly. So close your eyes for a second if this makes you dizzy. There we go. And we're going to fly over to the moon. And already, this is a good spot to check in with our human influence and how far we've gone out into space so far, because the moon is as far as humans have traveled out into space ourselves. The Apollo astronauts came out here back in the 60s and 70s, so about 50 years ago. And when they traveled to the moon, it took them about 2 days or so to get here, so we traveled much faster than they did. But this is as far as we've gone so far in terms of people walking around as our closest neighbor out here in space. And at the moon is where I like to introduce an idea that I'm going to be using for the rest of the show here, because we're going to be looking at incredible distances. Just the moon, even our closest neighbor, is about 250,000 miles away from us. So already we're very, very far away from the Earth. And as we go farther, we're going to see distances of millions and billions and trillions of miles and kilometers. So if I use those numbers as distance measurements, I don't know about you, but that's not going to make any sense to my brain at all. So from here on out, I'm going to use a different distance measurement. We're going to imagine that we are traveling the fastest speed we can possibly know of, the speed of light. And think about how long it would take us to get to these places if we were traveling at that incredible speed. So if we were traveling from the Earth to the moon, traveling at the speed of light, it would take us about 1.5 seconds. So we say the moon is about 1.5 light seconds away from us. So it would take about the same amount of time as it took us in open space to fly over to the moon if we were traveling at the speed of light in real life. But we're going to zoom back out again so we can continue on our journey. And I'm going to bring up some more lines here so we can keep track of the objects that we're looking at. So I'm going to bring up some orbit lines to show us where the moon orbits the Earth and then also where the planets orbit the sun. So you're seeing the orbit of the Earth as we go around the sun and the other planets in our solar system. And for a moment, I'm going to focus on the very center of our solar system, the closest star to us, the sun. Now, if we're still imagining this speed of light, the fastest speed we know of anything out there in the universe, if we were traveling at that incredible speed, it would take us about 8.5 minutes to get to the Earth, from the Earth to the sun. So about 8.5 light minutes of distance away from us. That's how far the sun is. And some people like to say that means, oh, if the sun just disappeared right now, we wouldn't know about it for 8.5 minutes. But thankfully, there's no reason why the sun would just disappear, so you don't have to worry about that too much. Another way I like to think of it is that if you walked outside right now and you looked at the sun, first of all, don't do that. Never look at the sun. But if you did look at the sun, that's how it looked 8.5 minutes ago. Not how it looks right now. And within these few light minutes of distance, we've got the rocky, smaller inner planets in our solar system, Mercury, Venus, Earth, and Mars. Now, there's a pretty sizable gap here in between Mars and the next planet, Jupiter, but that's not totally empty space. It just looks empty because these objects are very small. I have to make them really bright for us to be able to see them. That's where most of the asteroids are in our solar system. So the smaller rocky objects that we have mostly. Though not all of the asteroids orbit in the asteroid belt, but most of them do, in there between Mars and Jupiter. And then farther out still, we see Jupiter, Saturn, Uranus, and Neptune. And I'm going to fly us over really quick, just for a minute here, to my favorite dwarf planet in our solar system. And I'll bring up its orbit here as well. We're going to fly over real quick to Pluto. And I like to visit Pluto briefly when I go on these tours of our solar system and our universe because to this day, I still get lots of questions about Pluto. People ask me, what happened to Pluto? Did Pluto blow up? Is it still in our solar system? Why do you hate Pluto? But I'm here to tell you, I don't hate Pluto. I think Pluto is wonderful. And we have been calling it not a planet for quite a long time now. We're up to about 15 years that we've been calling Pluto a dwarf planet rather than a planet. But I don't think that makes it any less cool. And in fact, we know a lot about Pluto that we don't even know about some of the other places in our solar system, which is pretty awesome because we sent a spacecraft close to it just a few years ago, the New Horizons spacecraft. Which is why I like to fly up to Pluto up close because we have some really pretty high-resolution images of Pluto's surface. So I'm taking us around so we can see the heart of Pluto, it's sometimes called. It's kind of on its side over here. This white area that you see on the right side of Pluto looks kind of like a heart. We think there might be a slushy ocean of some sort under that heart. We know that Pluto has ice mountains and nitrogen snow and all sorts of very interesting, unusual stuff going on, which we did not know until we sent out a spacecraft, New Horizons, to fly by it. And the reason that we don't call Pluto a planet, why we call it a dwarf planet, has nothing to do with what Pluto's made of or how interesting it is. Really, it has mostly to do with just where it is in our solar system. If I zoom back out and we look at the orbit of Pluto, it's pretty far out, and it looks like there's nothing else out here by Pluto. But just like it looked like there wasn't an asteroid belt, there are quite a few objects out here. I just would have to make them brighter for you to be able to see them more easily. So I'm going to bring up some blue trails to show you some of these objects. It's going to look kind of bright, just a warning. They're going to show up kind of abruptly. There we go. And this is showing us some of the objects that are out by Pluto. And you can see that several of them are around where Pluto orbits in our solar system. So we didn't know about pretty much, I don't know if I want to say any of these, but most of these objects until the late 90s and early 2000s. And as astronomers started to find more and more objects out by Pluto, they began to question if we should add on more planets or if we should come up with a new category. So basically throughout that process, they decided that Pluto would be a dwarf planet because it has a lot of stuff in its orbit. But out here, I can show you as well the spacecraft that we sent out to Pluto, its trajectory, how far it has gone so far, as well as some of the fastest and farthest spacecraft that we have sent out into space. So each one of these yellow lines that I've put up here are the farthest spacecraft that we have sent out so far. So these are the Voyager 1 and 2 spacecraft, Pioneer 10 and 11, and New Horizons, which went out to Pluto back in 2015. But if we check back in with our light speed travel time here again, so we were taking 1.5 seconds to get to the moon, 8.5 minutes if we were to travel to the sun. And now if we were traveling at the speed of light and we were out here at the farthest any of our spacecraft have gone, we would not have been traveling for even a day at this point. So we're out to a few light hours of distance by now. But let's keep going because we have a lot more space to travel here. And we're now in the area that it's a little bit of a tricky question of whether or not we are still in our solar system or if we have left our solar system behind. Because the Voyager spacecraft, they're starting to be able to do some readings for us at their far away distance and see what the magnetic field of the sun is like out there. We might be outside of that at that point. But it's a little hard to define exactly where our solar system begins and where it ends. But out here, we've adjusted the brightness of the sun a little bit. We kind of dimmed it down before so you could actually see the other things in our solar system. But now the sun is at its true brightness, how it would look if you were this far out in space. And we're starting to fly past other stars. So at this point, I would say without a doubt, with any question whatsoever, we are outside of our solar system entirely. And we're starting to fly past other stars in our galaxy. But if we're going to check in again with how far we've gone at this point, if we were to travel to the closest star to us, which I think is on our bottom right now, over here, Proxima Centauri, which is part of the Alpha Centauri system, a few stars that are all part of the same star system together. Even with that being the closest star to us outside of our solar system, that would take us about 4 years to travel there. So things are very, very spread out here. There's a reason we call it space. There's a lot of space in between things. But there is one more opportunity that we have, even though we've gone farther than humans have traveled at this point, we've gone farther than our spacecraft have traveled. We have one more chance to check in with our human influence out here in space. Because while we have not sent any objects or spacecraft this far out, a few tens of light years away at this point, we have sent other things like, sorry, I thought it was farther than I was, like our radio signals. So this blue sphere that I've just brought up here is what we call the radiosphere. So we've been sending radio signals that are strong enough to escape our planet and that are traveling at the speed of light. We've sent those out into space since the 1930s or so. So if those radio signals didn't run into anything, which seems likely for most of them, since there's a lot of space in between things out here, they could have gone as far as about 90 light years from us in any direction. So that's how far anything we've sent out into space could have gone, about 90 light years away from us. But within that, and even around some of these stars that we're seeing out here, and all the things that we're going to see from here on out, we do know about these things because of the light that travels to us. So we don't know about these objects because we've sent someone there, we've sent a spacecraft there, but instead, the light of these objects traveled all this distance and got into our telescopes, and we were able to study it that way. And a very interesting type of object that we study out here with our telescopes are around many of the stars that we're seeing. So every single one of these blue markers that I've put up is showing us a star that has at least one exoplanet, what we call a planet that is outside of our solar system. And many of these stars have multiple exoplanets, just like our solar system has multiple planets too. And we've been finding exoplanets since the mid-90s, so only a little over 25 years now. But we're up to over 4,000 exoplanets that we have confirmed. And there's just as many what we call candidates for exoplanets. So things that we think are exoplanets, but we have to watch them a little bit longer to make sure that they are in fact a planet going around another star and not some other object like a really big sunspot on another star or something like that. So there are thousands and thousands of these out there, and possibly millions or billions more. Oh, but we still have a long ways to go, so I'm going to keep zooming us out here. Turned off the exoplanets, but I do like to keep on the radiosphere as we zoom away, see how long you can spot it as we zoom out. And now we're kind of transitioning over to a different kind of model, because all those stars and exoplanets that we were seeing there, all the individual dots and the markers to show us where the exoplanets are, we've mapped those out, and we've often taken actual pictures and images of those stars and places. But this is a model of what we think this object would look like, because like we saw, we have not gone out this far yet. So this is a model of what we think our Milky Way galaxy would look like if we could go outside of it. So this is based on what we can see in our galaxy and also what we see around other galaxies too. And I'll give you a second to look for the radiosphere. Can you still spot it? A little teeny tiny dot on the top left over there. That's how far any of our human communications have gone so far, just that little tiny spot. Well, we're going to keep on going because our galaxy is just one galaxy out here in the universe. As we zoom away from our galaxy, we are now seeing lots of other individual dots. And these individual dots, these are no longer individual stars, but instead individual galaxies. And we think that probably all of these galaxies have billions of stars. Some of them have trillions of stars. And we've mapped out where they are relative to us. Now, if you're wondering about the colors of these galaxies, these are not the colors of these actual galaxies, though I do think that would be fun if it looked like cosmic Skittles out there in the universe. But no, we've color-coded these galaxies based on what telescope found them. So maybe what kind of data set they're part of, or sometimes we group them together based on what group or cluster of galaxies that particular galaxy is part of. So we put things into different categories depending on where they are and how they were found and things like that. But this is an actual map. We've mapped out where these galaxies are relative to us. And because it is an actual map and it's from our perspective here on Earth, it looks a little bit strange if we get far enough out. So right around here, we're seeing a shape that looks kind of like a hourglass or a butterfly or a bow tie, something like that. Some people say it looks like pasta. Now again, the universe is not really shaped like a butterfly, though I think that would be delightful. This shape we're seeing is because we're looking at all this from our perspective, and we're in a galaxy. So that Milky Way galaxy that we saw before, it has gas, it has dust, it has stars, it has planets, it has all sorts of stuff in it. And so when we try to look in the directions of these big gaps that we're seeing on the top left and bottom right here, the galaxy we're living in is blocking our view. We can't really see over in those directions too well. So there are even more galaxies than this, and probably just as many galaxies in those gap directions as in the other directions. But we just haven't had a chance to map them out like we have with the ones that we're seeing here. And at this point, well, let's check in. We haven't checked in a while on how far we've gone if we were traveling at the speed of light. So we've made a big jump here. We went from a few light hours over by our solar system. I forgot to mention our galaxy is a few thousand light years across. So it takes us about 100,000 years to travel across our galaxy. And out here, I would guess we're a few billion light years away from Earth. Which brings up a cool point as well, which is that we're also kind of time traveling in a way when we look at these objects way out here in space. Because the way we see these is, again, because the light of these objects, these galaxies, is traveling to us and getting into our telescopes. So by the time the light travels to us and we see it, we're seeing these objects as they were billions of years ago, not how they look right now. So like I mentioned earlier, if you were to look at the sun, which again, do not look at the sun. It's really bad for your eyes. Never do that. But if you were to look at the sun, that's how it looked 8.5 minutes ago, not right now. So this is what our universe was like billions of years ago. And because of that, that means that there's only so far that I can take us. There is an edge to everything we can see in our entire universe. And that edge of our observable universe is going to show up all over the dome here in just a moment, what we call the cosmic microwave background. Now, when you walk outside, and if it's a clear night and you look up at the stars in the sky, you're not going to see this every single place you look in the sky. Thank goodness, that would scare me if you looked up in the sky and saw this everywhere. But if you could see with microwave light, a lower energy form of light that our eyes can't see, but our telescopes can, you would see this every single place you look. And actually, yesterday marks kind of an anniversary for the cosmic microwave background. In 1965, that was the first time that some scientists discovered this cosmic microwave background and confirmed that it was light out in the universe that they were seeing. It was kind of confusing at first. They looked up with their radio telescope and said, why am I getting this weird interference everywhere I look over the sky? But it turns out this is actual light from early in the universe. So this is a few 100,000 years after when the Big Bang would have happened, when light was able to spread out in all directions. So I like to refer to it as the baby picture of our universe, the earliest light that we can see. But since this is as far as we can see in our universe, that means I can't really take you any farther. So we're going to end our journey by flying back home. I'm not going to leave you stranded out here in space. And keep in mind, if we were really taking this journey and if we were really traveling at the speed of light and really this far away, this journey back would take us about 13.5 billion years. But don't worry, we're in the planetarium. It should only take us a minute or two. And one last thing I want to leave us with as we fly on back home is that all of this that we've been looking at, all of these stars, galaxies, cosmic microwave background, planets, dwarf planets, everything we can see, is not even everything that we know to be in our universe. There's some really mysterious things like dark energy, some mysterious force that is causing space itself to accelerate as it expands. There's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it a lot of different places in the universe. And we call these things dark energy and dark matter because we're not quite sure what they are, but we do know that they make up about 96% of our universe. So all this that we can see is a very tiny portion of everything we know to be out there. And I know that that can make folks feel kind of small and uncomfortable. And I agree, I feel uncomfortable with that idea sometimes too. But another way I like to think of it is, well, sure, we are this one little tiny dot, but look at all of this that we have found so far, almost entirely by just looking through telescopes. And there is a whole lot more to discover and a whole lot more to learn about out there. So that's pretty exciting. But still, with how exciting that is, I'm always a bit relieved when we get back to our radiosphere, back to our human realm of the universe out here. And we're going to zoom on back to the closest star to us, the sun. And we'll end our journey where we started, at that third planet from the sun, which, by the way, is the only place in all of this that we have found life at all so far, which is another pretty incredible thing to think about. And we're back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying around in space with me, and I hope you all enjoy the rest of your day. Thank you so much for coming.